So in this next section, we're going to talk about properties of logs. A lot of times people don't really understand why we need to be able to manipulate logarithms, but when it comes time to solving equations involving logarithms, also, if you move on to the calculus stage, it's very important to be able to manipulate a logarithmic expression so that you can do different types of differentiation and integration, and there's lots of reasons why you would need to be able to manipulate logarithmic expressions. Three of the most, I would say, prominent properties that you would need to know involving logarithms are the product rule, the quotient rule, and the power rule. The product rule says that if you are adding two logs of the same base, that this sum will be the same as if you have a log of the same base with those values, with those arguments multiplied. Okay, so for any xy, and where xy are positive real numbers, and b not equal to 1, all of these things, it would be true that the sum of these logs is equal to the log of the product of those arguments. The quotient rule says that if you are subtracting two logs of the same base, that this difference would be equal to a log of base b, the same base, with the argument of the first divided by the argument of the second. And then finally, the power rule, if you have a logarithm where the argument is being raised to a power, you would get the same thing evaluating this as if you multiply log base b of x by that power r. Okay, so let's just work on manipulations. And like I said, right now we're just basically going to be practicing our manipulations. We'll see why it's necessary more when we move on to the next section when we're solving these logarithmic equations. Okay, so here we want to rewrite this as a single logarithm. Okay, so here we have the sum of two logarithms, both have the same base. And if we remember, going back to the previous slide, this says that if I am adding two logs of the same base, that this sum is the same as log base b of x times y. So, log base 2 of x plus log base 2 of y, according to the product rule, is the same as log base 2 of x times y. Right? This is according to, or we use, the product rule to do this. And so what we've taken is this expression involving two logs, and we've rewritten it as a single logarithm. So that's what it means, just a single logarithmic term. Okay, here we've got the natural log of 5x, and we want to rewrite it as the sum of two or more logs. So I want to take this single logarithm and I want to split it up so that I have two or more. Okay, and so how I'm going to split it depends on the operation in the argument. So within the argument, this 5x, that's the same thing as 5 times x. So if I have a multiplication or a product, then I would use the product rule to separate. So the product rule says that this is the same as the natural log of 5 plus the natural log of x. So I have taken and written that single log as the sum of two logarithms. Okay, we want to rewrite this as a single log and simplify if possible. So we'll first focus on rewriting it as a single log. So looking at what I have a difference of 2 logs of base 2. So it's because they have the same base that I can do this. And because it's a subtraction, I'm going to use my quotient rule. So we have, according to the quotient rule, log base 2 of 40 minus log base 2 of 5 is the same as log base 2 of 40 over 5. And I can simplify that. 40 divided by 5, that's 8. So this is the same thing as log base 2 of 8. And as I'm going through these, if I end up with a logarithm that I can evaluate, I will. Remember, log base 2 of 8 represents what 2 would be raised to get 8. Since that's something I can do easily enough without, getting some crazy decimal number, I'm going to go ahead and do it. That power is 3, right? Log base 2 of 8 represents the power 2 must be raised to get 8. That power is 3. And so it's nice, you can see, when you're using these these properties of logs, you can take two, sometimes you've been giving something that you can't really figure out by hand. So if I'm looking at log base 2 of 40, and I'm trying to decide what I would need to raise 2 to get 40, well, that's not something I can guesstimate, but I can't say for sure because 40 is not a power of 2. Same thing here, log base 2 of 5. 5 isn't a power of 2, so I don't know for sure. I do know, this would be a value between 2 and 3, because 2 squared would be 4 and 2 to the third is 8. And also here, I know that this would be a value between 5 and 6, because 2 to the 5th power is 32, and 2 to the 6th power is 64. So I know, ballpark, but I can find the exact value of this difference without ever having to reach for my calculator. Okay? Here, rewrite log base 9 of 81xy over zw in terms of 2 or more logarithms and simplify. Assume all variables are positive real numbers. Okay, so looking at this, so I'm trying to split it apart. So when I'm splitting it apart, I look at my argument. I have multiplication and I have division. When I have both multiplication and division, I always rewrite it using the quotient rule first. So using the quotient rule, this would be log base 9 of 81xy minus log base 9 of zw. Okay? And so when I'm trying to split it apart or writing it in terms of 2 or more, you need to keep going until you have your arguments as just single factors with no powers. Okay, so here I've got 81 times x times y. So since I have these 3 factors, I know I can rewrite this as the sum of 3 logarithms. So so here I used the quotient rule. And now I can use the the product rule, since I have multiplication, to separate it further. So this would be log base 9 of 81 plus log base 9 of x plus log base 9 of y. And that's that first. That's this, all split apart, minus, when I split this apart, I have log base 9 of z plus log base 9 of w. Okay? And then coming back, this first set of parentheses is really, not essential, but the second set of parentheses is, because we are subtracting this whole value here. And when we split that apart into 2 terms, we need to make sure that we subtract each of those terms. So going through and simplifying further, I've got log base 9 of 81. If I come across a logarithm that I can easily evaluate, I do. I know that if I take 9 to the second power, that I'm going to get 81. So log base 9 of 81 is 2. So this is 2 plus log base 9 of x plus log base 9 of y. Again, we need to make sure that we subtract each term. So that would be minus log base 9 of z minus log base 9 of w. So we've basically taken this and split it all apart so that we have just single factor arguments and with no powers. Okay, so anytime it basically says rewrite it as 2 or more, you need to keep going until all of your arguments are single factors, no variables. Okay? So here we want to expand. That means the same thing as writing it in 2 or more. Log base 2 of 16x to the 5th y to the 12th. Simplify if possible. Assume all variables represent real numbers, positive real numbers. And we need to say this in order for our properties of logs to hold. Okay, so as we go on from here, so we've got log base 2 of 16x to the 5th y to the 12th. So this is my argument. So I've got multiplication and I've got powers. I'm going to focus on breaking it up using the product rule first. So according to the product rule, this is the same as log base 2 of 16 plus log base 2 of x to the 5th plus log base 2 of y to the 12th. Okay, so that is a single factor argument. Here I have a single factor, but it's being raised to the 5th power. So if any of my arguments are being raised to exponents, when I'm trying to do the expansion, I want to then follow up with the power rule, which says I can bring this x to this power of 5 down as a coefficient. Let me go back to that very first slide. The power rule says that if your log has an argument that's being raised to a power, then you can rewrite it with that power as a coefficient. Okay? R times log base b of x. And it makes sense. You know, if you think about what this says, log base b of x to the r, that's the same thing as log base b of x times x times x times x. Right? And you multiply that r times. And so if we rewrote this using the power rule, we would have log base b of x plus log base b, can't write today, of x plus so on and so on until we have all r written out. So if I add something r times, that's the same thing as multiplying it by r. Okay? So here we are. So if the argument has a power, you can write that out front as a coefficient. So as I go through, log base 2 of 16, again, that's something I can evaluate. If I take 2 to the 4th power, I will get 16. So log base 2 of 16 is 4. Bringing my 5 down as a coefficient, this would be 5 times log base 2 of x plus, bringing down the 12, that's 12 times log base 2 of y. So this is what it looks like, fully expanded and simplified. Okay. Here, rewrite this as a single log and assume all variables are positive real numbers. So now we're going to go back to single. So we're trying to put it all together again. And if I'm going through trying to rewrite it as a single, I always look first for, do I need to put those coefficients up as powers? So first thing, when you're putting it back together, I always use the power rule if I need to. And I need to if I have coefficients. Okay? 1/2 times the log of x is the same thing as the log of x to the 1/2 plus 4 times log of y, according to the power rule, is the same thing as the log of y to the 4th. Okay? And please don't put these as subscripts. There is no base, which means the base is 10. If you write either of these as subscripts, then you're changing the base of the logarithm. So these are arguments. They should be written in line with the log. And then this is minus the log of z to the 3rd. And once I've taken care of those coefficients, then I can use the power rule and the quotient rule as necessary. Okay? So here I have an addition, and here I have a subtraction. So putting it back together, basically, if you have a series of additions and subtractions, if you think about using the product rule and the quotient rule together, if the term is positive, it's going to be a factor of the numerator and you're put together. If the term is negative, it's going to end up being a factor of the denominator. So I use my product rule or my quotient rule as needed. Okay, so log of x to the 1/2 plus log of y to the 4th is the same thing as log of x to the 1/2 times y to the 4th. And this minus this, now I can use the quotient rule. So that's the same thing as the log of, and instead of writing x to the 1/2, I'm going to write that as the square root of x. That's how you'll see it more in your homework. So that's the square root of x, y to the 4th, all over z to the 3rd. Okay? So, to get from here to here, I use the power rule. To get from here to here, since I was adding two logs of the same base, I use the product rule to put it together. And here I have this minus this, so if it's a subtraction, then I can use the quotient rule. And I have now rewritten this as a single log, right? There's only one single logarithmic term. We also have the change of base property, which is very useful when you're trying to evaluate logs that have bases other than base 10 or base e. The change of base says if you have log base b of x, that's the same thing as log base a of x divided by the log base a of b. The change of base basically says a can be any number you want. So you can find the value of this logarithm by changing your base to whatever you want. But it always has to be, regardless of the base, it's always the logarithm of this argument divided by the log of the base. Okay? So let's look at an example. So if I want to find log base 4 of 42, now if you go through and you try to calculate what log base 4 of 42 is, if you go through the powers of 4, 4 squared is 16, 4 to the 3rd is 64, etc., etc. So therefore, if I'm trying to decide what I would have to raise 4 to in order to get 42, based on what I have here, I know that this is going to be some crazy number between 2 and 3. I just don't know at this point what that number is. I can, however, find this using the change of base. And if you want to be able to use your calculator, then you would need to choose a base 10 or choose a base of e. So if we want to decide or find the value log base 4 of 42, then if I did a base 10, that would be the log of 42 divided by the log of 4, again, using my change of base formula. So I chose A to be 10, so I have log base 10 of 42 divided by log base 2 of 4, because 4 was my base and 42 was my argument. But because I use base 10, again, we don't usually write base 10. But I chose base 10 because I have a base 10 button on my calculator. Okay, so log of 42, and again, make sure that you close your argument, the parenthesis, divided by the log of 4. That gives me 2.696. Okay, so this is approximately 2.696. Let's try that again. 2.696. And I am seeing that I'm getting a value between 2 and 3, which is what I expected. Okay? But according to change of base, it shouldn't matter what I choose as my base. It shouldn't matter if I choose 10 or if I choose E. I still should get the same thing. So if I choose base E, then I have log base 4 of 42 equals the natural log of 42 divided by the natural log of 4. So using my calculator again, because I do have a natural log button, so using my natural log button on the calculator, got the natural log of 42 divided by the natural log of 4, and again, I get the same value. So it doesn't matter what you use as your base. But in general, it's easiest to use 10 or E. Of course, if these two numbers can be written in terms of the same base, you know, you could choose that base instead. Other helpful properties. Log base b of b to the r equals r. Well, that should be self-explanatory. You know, if we're not even looking at this side over here, remember a log represents what you would raise the base to get the argument. So what would I raise b to get b to the r? And that would be r, right? Also, b to the log base b of x is x. And this one's a little bit trickier for people to understand, but to understand it, you have to kind of come back here. Again, log base b of x represents what b would be raised to get x. Okay, it is the power b is raised to get x. And so if I take b and I raise it to the power b is raised to get x, I am going to get x. And sometimes that takes a little bit of thought. So if you're not getting it right now, just kind of think on it a little bit and hopefully it'll come. So if I want to simplify log base t of t to the 8th, according to my property and according to logic, this is 8, right? What do I raise t to get t to the 8th? I raise it to the 8th power. Also, 6 raised to log base 6 of 16. Again, log base 6 of 16, this is the power 6 is raised to get 16. So if I'm going to take 6 and I'm going to raise it to that power, then I am going to get 16. So that's all for now. You know, really you're just going to have to kind of work through the homework a little bit and practice using those properties to expand or reduce to a single term. You just need to make sure that you're actively reading when you're doing your homework, that you're reading the directions and doing what you are asked to do. Good luck!